I'd like to take a look at section 4.6. This is on numerical integration. So in some applications, it is impossible to find an antiderivative of a given function and use the fundamental theorem of calculus. Remember, the fundamental theorem of calculus says that if we want to compute an area, I can take the integral of a function, find its antiderivative, and then plug in the bounds. But that requires us to be able to find the antiderivative. So if we can't find it, we have to come up with a different way to at least approximate it, to get some estimate of what we think that area would be. So we used rectangles. This was a way to approximate areas. So all we did, right, so if we think about in this region, say if I want to find the area from A to B underneath this curve, I could just define these little horizontal lines, right? We could use, say, the right endpoint and then be able to define those. We could use the left endpoint. If you want to, you could use the midpoint and come up with those. So we could use rectangles as a way. All that's doing is just creating this constant, this horizontal line. But as a way to improve this, we can instead use trapezoids. So a trapezoid in this region, what it could look like is I would instead just connect these two with a straight line. And then I would connect these two endpoints with a straight line. So on each of the intervals, I am forming this trapezoid that then I could calculate the area of this trapezoid and add those together. So instead of taking a constant as the top of this, we can instead take some type of slanted line. Obviously, it could be flat or it could be a slanted line. So that's one way to improve this, is using the shape trapezoids, which use this linear approximation on the top. So this is called the trapezoid method. So some information to get us comfortable with this is the width of each of these. We're assuming that we're going to use constant widths. So the same widths across the board, the same way we did with rectangles. We'd like that uniform way of defining the widths. The area of a trapezoid, in case it's been a long time since you remember areas, if we have a trapezoid where this is the two different heights and that's the width, the area is going to be the average of these two heights times the width. So you take these two, add them together, and divide by 2. Maybe you've seen this with like B1, B2, and H. Whatever variables you're used to, it's still the same computation. So some notation that we're going to become familiar with is we're going to use this endpoint notation to say that we're going to have subscripts to indicate where each of our endpoints will be in our region. So what this means is that this first endpoint where we're starting, we're going to call that x sub 0. Then wherever the next way that we're going to define this, we're going to put an x sub 1 there. Then the next width, or this next cutoff endpoint here, we're going to call this x sub 2. The next one, we would call this, say, x sub 3. And however many rectangles we're using, we're going to have n rectangles, so that n is the same up here as that n. However many rectangles, that's going to define this last one as x sub n. So if we had 5 rectangles, that would be x sub 5. So what this allows us to do with this notation is that we can now write down a formula that would calculate the total area present. So we can calculate the area of each of these trapezoids using this formula with this notation. So the area of my first trapezoid, we see that's going to be this first height plus this other height divided by 2. So this one, we see the height of this is going to be f at x sub 0, and this one is going to be f of x sub 1. That's the height on the curve for each of these. So I have f of x sub 0 plus f of x sub 1. I divide that by 2. That's this part of my formula for the trapezoid times the width. The width we defined as b minus a divided by n. Times b minus a divided by n. So that's for the first trapezoid. Then we can repeat this for all of the other trapezoids. So the next trapezoid we see would be f of x sub 1 plus f of x sub 2 divided by 2 times b minus a divided by n. Now, because again, we use the height of this one, this left side, plus the height of the right side. So that's how we got f of x sub 1 plus f of x sub 2. And then we divide that by 2. And so on and so forth until we get to this last trapezoid here. So this would be x sub n minus 1. So I have f of x sub n minus 1 plus f of x sub n divided by 2 times b minus a divided by n. Now we can start to simplify this because anytime you have this large sum, we could use summation notation if we wanted to. We want to be able to simplify this. So notice this is a sum of a whole bunch of things where there's some terms that are repeated in all of them, right? Every single term has a b minus a divided by n present. And every single term has a 1/2 present. So I'm going to factor that out. So I have b minus a divided by 2n. Then what I'm left with, and when I take out the b minus a divided by n and this 2, this first term I'm left with an f of x sub 0 plus f of x sub 1. So I have f of x sub 0 plus f of x sub 1. Then this next one, I'm left with an f of x sub 1 plus f of x sub 2. And so on and so forth. The next one would have f of x sub 2 plus f of x sub 3. And then I keep doing that all the way until I get to the very last one. That's going to have my f of x sub n minus 1 plus f of x sub n. So I'm adding on all of these function values, but notice some of them appear more often than others. Notice that this f of x sub 0 only appears once, but this appears twice for f of x sub 1. F of x sub 2 will also appear twice, because if we go back to this, what we're using is this height over here once for this first trapezoid. But this height over here for this function value at x sub 1, that gets used as the right side of this first trapezoid, but it also gets used as the left side of the second trapezoid. Same thing with this one. This also gets used twice. Once for this trapezoid and once for this trapezoid. And then all of them get used twice until we get to the very last one that only gets used once. So what this can now be summarized as is f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus all of these plus 2 times f of x sub n minus 1 plus f of x sub n. And so this is going to be the fastest way for us to compute the trapezoid method by using this formula. We just plug in the function values here for all of those, and then we multiply some of them by 2, and then we add all of these together, multiply by b minus a divided by 2n. Now, this is going to be one where we're going to usually work with small numbers of rectangles. So the summation notation that we use for rectangles, that allowed us to eventually take limits. We're not going to be taking limits with the trapezoid method. We're simply going to say, what if I have 4 trapezoids? What if I have 7? What if I have 9 trapezoids? And we'll just compute this by hand without the need for summation notation. So we'll do some examples of this so you can become familiar and comfortable with how do we apply this to specific problems.